on the other side maybe never finish, because it's not, because there's no way to compute it. Okay, how does that work? As you can see here, on the left side, there are some of the trees which might be found by the algorithms. And now we are trying to match those with the tree on the right side. And I'm pretty sure that you can really fast spot the match here and have find the tree that exactly matches this operation. That is basically what we do. For most of the gadgets, we kind of like use a fuzzy algorithm so that not all of the leaf nodes have to be of any specific kind, so that we can find more gadgets that essentially, though, do the same work for us. So we are not only looking for a memory store to a register, but also for a memory store to a register plus a small or even large offset, because we can still have the value in the register pre-computed in the compiler, so that the addition of the small or the subtraction of the small offset then gets reversed in effect. Okay, to select the simplest gadget, what does that actually mean? For most of the instructions, like in addition, we have trees that can be arbitrarily complex, but there are also trees which are very simple, and we try to strip down most of the very large and very complex trees, because they are really hard to compile later on because of all the side effects I told you about already. Okay, what I have shown you in the last 15 minutes, algorithms which automatically extract gadgets platform independent for return-oriented programming are feasible and possible. So you can work with those algorithms by using REIL on multiple platforms, and you will get usable results. Also, all the gadgets that in the primary definition of return-oriented gadget, in return-oriented programming, the Turing completeness in this case, is satisfied. And also, you always have to think about that searching for those gadgets is very, very platform and very, very compiler dependent. So for the ARM gadget set, which we have tested on various devices, given that the compiler changes, like some of the gadgets which are more complex than a normal addition get emitted from the compiler differently on iPhone than they would get on Windows Mobile. So you always have to have the fuzzy tree matching in place there to be able to find everything that you later need to have the Turing complete gadget set. Okay, so what's next? Next, I'm gonna give over to Ralf as Mr. Wolf, and he's gonna show you how to combine those gadgets.
Okay, so what's chaining gadgets like? It's a lot like playing Tetris with very ugly pieces. Actually, for the iPhone, the pieces are not so ugly, so it's a regular Tetris game. But if you tried, for instance, exploiting something on Symbian and you wanted to build your gadget set just on euser.dll, which is the most basic library that you can have there, it would get very nasty. You'd get very nasty pieces. And playing Tetris by hand with very ugly blocks is not something that we enjoy doing. So where does this complexity come from? So basically each gadget set that you have defines a custom instruction set architecture. So whenever the version of your library changes, or maybe there's a compiler change, Apple has switched the GCC to CLang, you will have a new gadget set. However, we have better scores at piecing together Tetris than this. Nonetheless, it has become difficult in some cases, hence we have decided to bring in some help. This help is Mr. Wolf. So, Mr. Wolf is a ROP compiler for gadget sets with side effects. So, you may wonder why you haven't seen anything about this before. It's interesting. So there are a number of academic papers on return-oriented programming, but they all consider the case where they don't have side effects because they don't deem that interesting. What we have found is that if you want to automate this process on most RISC architectures where you don't have unintended instruction sequences as you have on x86, you will have to deal with side effects. And hence, we have built the Wolf. So at the moment, the Wolf is only for ARM, but it's about a weekend of effort to port it to another architecture. It's a very basic language that we use, or that you use if you want to use the Wolf. And at the moment, it's kind of a prototype that's implemented in Python. This probably will change in the future if I understand things correctly. So to live with side effects, you have to adapt the language that you program in. So what we do is we give the programmer several opportunities to tell the compiler what he may do, what things he can, like what registers he can clobber. So all of the registers that the compiler is not allowed to clobber, you protect. So the protect statement is given a list of registers, and between two protect statements, these registers will stay invariant, except if they're explicitly modified by the assignments you do in between. The allow read statement gives you the opportunity to tell the compiler which memory ranges are okay to touch for reading without triggering any page faults. And the allow corrupt statement gives you the opportunity to tell the compiler which memory ranges he can actually overwrite, which are basically expendable to you. So you may or may not repair them later. Okay, now operational side. What kind of statements do you have in the language? It's a very, very simple language. So the most important construct that we have is a multi-assignment. So this means that you basically have a tuple of components on the left-hand side and on the right-hand side. You'll see it on one of the next slides. Then we have a conditional go-to statement, which you will need if you want to have loops. And this conditional go-to statement is very simple. It's a go-to if non-zero. So what you pass it is basically a register or a memory location that, if it is non-zero, will trigger a jump to a label. And the other thing that we have is a call statement for interfacing with native library functions. The other two things are data definitions, obviously. You may want to have some of those in your code as well. And obviously you need to have then labels for these data definitions and for the code if you want to make use of the conditional go-to statement. So how does one of these multi-assignments look like? This is from the Pwn2Own contest. So this is the payload translated back into our language. This is just one of the statements that is in this. So the full payload you see in the white paper. So this is basically the setup that you do in the registers before you do the connect call. So what you do there is you have 3 target registers of 0 to R2 that will be assigned to first a, well, basically a star pointer. So you do a memory read here. So you read the memory at the address socklock, which was where you previously stored a file descriptor for the socket that you opened. Then as a second argument, which goes into R1, you have the data reference to the sock address in that you have defined. And the third is just a constant assignment of the size of this struct into R2. So you will notice this kind of funny thing in between that we use as an assignment operator. This is a very nasty hack because you cannot overload the assignment operator in Python. Okay, a loop is a very simple thing as well. You define the label for the loop. You define a counter. In this case, it's a register. Then we're doing something kind of nonsensical, but maybe pedagogical. So what you do is you assign a range of memory of 1024 bytes to 0, so you just clear a range of memory, and at the same time you compute multiples of the register R1, which is basically going down from 256 to 1, and you compute that in the register R2. So what you'll notice here is that the right-hand side of this multi-assignment contains the computations. So this is how you actually perform arithmetic logical calculations in this language. So all of them will be done in assignments or multi-assignments. Okay, so now we come to the actual implementation of the Wolf. So Mr. Wolf is a very high-level problem solver. He likes to delegate and he likes to have his things done fast. So what we did in this case was we used a tool called STP, with a simple theorem improver, to do the manual work for us. So STP, some of you may be familiar with. It's a constraint solver for problems involving bit vectors and arrays. It's an open source tool that was written by an MIT researcher called Vijay Ganesh, and previously it has been used for model checking, theory improving, EXO, which is a paper about constructing so-called inputs of depth, and other things in the security community. So what it does is basically you give it a formula in this theory of bit vectors and arrays, and STP will tell you whether this formula is satisfiable or not, and if it is satisfiable, it will tell you an assignment. So an STP formula is just a bunch of assertions in this theory, which is called the quantifier-free theory of arrays and bit vectors. So this is actually, there are a number of theories that you can build these solvers for, and this is one of them. So there are yearly competitions for these. It's called SMT, satisfiability modular theory, and this is one of the simple modes that you can deal with. So a simple example in this STP language would be just an assertion for a simple formula that just involves additions and multiplications. Obviously, that's very simple. Usually, we will have much bigger things. So this is just 10 different variables of 4 bits each. So what we do is we translate the expression trees that Tim has spoken about into STP formula in the algorithm that we use. And I will now give you a high-level description of this algorithm. And I will specifically concentrate on the multi-assignment because compared to the other things that we had to do to get the Wolf operational, the multi-assignments were the most work. So what you do to generate ROP code for multi-assignment is